Guys, welcome back. We're going to do second lecture for chapter 12 here. This is a slide I left off with last time. So we talked about this carbon dioxide coming out of this lake. So we're going to move on to colligative properties. We're looking at non-electrolyte solutions, so ones that generally aren't going to conduct electricity. Colligative properties are properties that depend only on the number of solute particles in solution and not on the nature of the solute particles. So basically that means it could be sodium chloride or calcium chloride or strontium chloride or sugar or just about anything. As long as there are more solutes, it's going to affect the colligative properties. So vapor pressure lowering is one effect here. We use Raoult's law to show this. P1 naught here is the vapor pressure of the pure solvent. So if we were dissolving, I don't know, salt in water, this would be the vapor pressure of just pure water. And then X1, you might remember this from earlier in the year actually, we use the same symbol and everything, is the mole fraction of the solvent. So not the solute, the solvent. So if the solution contains only one solute, then X1 is equal to 1 minus X2. And then we can solve for this P1, 0, which is the vapor pressure of the pure solvent, minus P sub 1, which is our pressure, vapor pressure lowered, is equal to delta P. And so delta P is equal to X2 P1, which was the vapor pressure of the pure solvent. And X2 is the mole fraction of the solute. So X1, mole fraction of the water, X2, mole fraction of the salt. And hopefully you'll recall to do a mole fraction, you take the moles of what you're interested in divided by the total moles in the whole system. So here's a graph for benzene. Benzene's pressure plus toluene's pressure gives us total pressure, and total pressure is the solid red line here. And so here just shows you the pressure of A, which could be benzene, is the mole fraction of benzene plus the pressure of just the solvent, whatever that could be. It could be benzene, maybe toluene, I don't know, PB, so the second one, toluene, is equal to the mole fraction of toluene times the partial pressure of toluene. And so then total is A plus B. The pressures of benzene plus the pressures of toluene give us the total pressure that we're measuring. And so this is important because what it's showing us is it depends not only on the pressure exerted by a certain chemical, but it also tells us that the pressure that we're observing in the lab is actually a result of the pressure of that solvent multiplied by the mole fraction that solute makes up, because it's not just how much pressure it exerts, but it's how many moles of the total solution belongs to toluene. So we take that into account here with this formula. This is just to show you that this solid black line is our line predicted by Raoult's law, and then here's the dotted lines for substance A, and then here's the dotted line for substance B, and this is ideal situation. Here's what it should look like. Sometimes in a lab setting, that's not really what's going to be going on. If the force of attraction between the molecules for the solvent and the solute are, less than the force that's holding the individual solute molecules together and the individual solvent molecules together, our graph can look a little bit different. And then here's the opposite situation, although we are very, very close here. Predicted by Raoult's law, solid black lines. Here we've got the force between our solute and solvent is much greater than the force holding the solute together and the solvent to other solvents. So we get a total pressure that's a little bit lower than we thought we should get with Raoult's law. Not a big deal. It just shows us that in an ideal situation for our calculations, these black lines, we're getting these assuming that our solute and solvent are equally attracted to each other as they are attracted to other solute molecules. And sometimes that's not the case, so we do get some deviation from ideal. This is just a diagram of a fractional distillation apparatus. Basically, things will boil off at different temperatures, so our least dense thing boils off first, and then it condenses as a gas, and then we get this gas condensed here, and then the next most dense thing boils off. And that's pretty cool because it's super important way we can distill all sorts of things we manufacture. Here's another example of a colligative property, and hopefully we'll get a chance to see this in the lab. It's boiling point elevation. And basically the idea is oceans don't readily freeze because there's a lot of salt in the ocean. So as you add more solute, the boiling point, which is a colligative property and depends only upon the concentration of solutes, is going to increase. It's a lot harder to boil ocean water than it is to boil pure water. It's also a lot harder to freeze ocean water than it is to freeze pure water because these things are colligative properties. So there's a little graph to show you how we've changed boiling point of water here and the boiling point of water in solution. We have increased that because this is temperature on the x-axis. So here's the formula that we use for this. TB naught is the boiling point of pure solvents, that'd be just water. TB is the boiling point of the solution, that'd be salt water. And so delta T is the difference, so it's not really that amazing, delta T is just change. So if pure water boils at 100 degrees Celsius and a certain concentration of salt water boils at 101 degrees Celsius, then our delta T is 1 degree Celsius. That's really all there is to it. So here's the formula that we're going to use quite a bit actually this chapter, and this is going to get us through a lot of questions. But the delta T sub B, which is our boiling point of our solution, is equal to this constant. This constant's K sub B. It's the molal boiling point elevation constant for a given solvent. I want to star that in your notes. Don't spend a lot of time Googling molal boiling point for salt. No, it's for the solvent, so it's for water, or it's for benzene. It's whatever the normally liquid we're doing our dissolving in. That's what we're going to look up. Table like 12.2 or something like that in your book has like 5 or 6 of these. And then M is molality. Hopefully you remember that molality is moles per kilogram. Not moles per liter, that was molarity. Moles per kilogram solvent is the molality of the solution. So then we can use this equation, and it's nice because if we have these two, we can solve for a change in temperature. If we find the change in temperature, we can solve for molality. It's pretty easy and it's pretty linear to work with, so you'll definitely want to have this thing in your notes somewhere. It's an important formula. Okay, so now we looked at boiling point elevation. Now we can look at freezing point depression. Kind of the same idea. Here's your pure water freezing, 0 degrees Celsius or whatever. Now we put a bunch of salt in the water. We try to freeze that. We end up getting, -2, -3 degrees Celsius. That's lowering the freezing point. This is kind of how, ice cream is made, which is nice. So again, same thing. The delta T of, freezing point is the pure solvent minus the solution. And so we get this. It's very similar to boiling point. The change in temperature of our freezing point is equal to the constant times the molality of our solution. And that's all it is. M is molality of the solution. Kf is a molal freezing point depression constant. It's in the same table as K sub B. You just got to make sure you're using the right one. If it's freezing point depression, you want to find Kf. Boiling point elevation, you want to find Kb. Their units are degrees Celsius per M for molality, so it's not too bad. And here's your table. Like I said, it doesn't cover a whole lot, 5 of these things, and it just gives you your solvent. The normal freezing point, if you have the pure solvent, is right here, and then our Kf in degrees Celsius per mole, and then our normal boiling point, and then our boiling point constant. So pretty straightforward, pretty easy to work with, and we're going to work with it a lot. So here's an example of how you could do a question like this. What's the freezing point of a solution containing 478 grams of ethylene glycol and 3202 grams of water? The molar mass of ethylene glycol is 62.01 grams. And so we know that water is our solvent because there's a lot more water than there is ethylene glycol. And so our goal is to find the freezing point. And so if we're going to find the freezing point, we want to find our change in temperature freezing, and that's equal to our constant times our molality. And so bear in mind that you got to kind of start with some knowledge. What's water normally going to freeze at? Probably about 0 degrees Celsius. And so when we find freezing point depression, they're assuming we already know if you're depressing a freezing point, you're making that temperature colder. So don't be fooled by lack of negative signs in our equations. You have to know freezing point gets colder, boiling point gets hotter, that kind of stuff. So we go to that table, 12.2, which we just left, and we find the Kf of water is 1.86, and that's a constant. Now we got to find molality of ethylene glycol in water. And so molality is moles of solute. Well, that won't be too bad. We just take grams and convert it to moles. And then our mass of our solvent, and our solvent is water, and that's nice because it's in grams, so we're already pretty much ready to go there. And so we take our 478 grams of ethylene glycol, and we look up what ethylene glycol is made up of, and we go 62.01 grams per mole from our periodic table. That gives us moles. And then 3.2 kilograms of solvent. We just converted grams to kilograms, divided by 1,000, 3. And we get 2.41 mole. And so 2.41 multiplied by this gives us our change in our temperature. And there it is, 1.86, the constant from the table, 2.41, molality that we calculated. Little m cancels out, you're left with degrees Celsius, 4.48 degrees Celsius. So you say, okay, that's the change in the temperature that we freeze at. That's change in freezing temperature, not the end answer. Don't get excited and get these wrong because you think you're done. Water normally freezes at 0. So now we say, okay, our change in temperature is the temperature that we calculated minus our temperature that water would normally freeze at. And so we say, okay, water would normally freeze at 0. We made it 4 degrees difference, and since it's freezing point depression, it's 4 degrees lower, so it's negative 4 degrees Celsius. Then we're done. Okay, so we're going to get a lot of practice in those. So osmotic pressure, we're not going to get into that just yet, because even though we've only covered a little bit of ground, we've actually got enough material to do a lot of questions. So that's going to be it for today.